In today's video, we're going to function on logarithmic function data modeling and the semi-log plots. And so we're going to start with this graph up here. It says the average salary for a church pastor across the US increases as the size of the church increases. The graph above shows the average pastor salaries for various church sizes. We can clearly see a pattern in the data, but the models we've used previously are not appropriate for this data. The graph above displays a large rate of change at the beginning. So when we're starting here, there's a larger rate of change. As we start moving this way, our rate of change slows down. And so that models a logarithmic function. Just as we've seen other types of functions, linear, quadratic, and exponential, and so on, in real-world scenarios, we have some that follow a logarithmic pattern. Outside the salary data in the graph above, we see that pattern. So it tells us logarithmic function models. For a given set of data, if the input values appear to change proportionally over equal length output value intervals, then a logarithmic model is appropriate. So we had talked about that. If our x values or our independent have that common multiplier, it's logarithmic. Just as a quick reminder, if the y values had a common multiplier, that was the exponential. And so a logarithmic function model has the form of y equals a times b to the natural log of x, or y equals a times b to the log x. Both of those would be the ones we most commonly use. That's our natural log and our common log. Remember, the common log has a base of 10. So here is a table of values. It says use the given data to write two equations that can be used to find the values of constants a and b in the expression for L of x. So we're going to look at this model here, and we'll go back to that data up there. But right now we're going to start with this right here. And so the reason why it tells us to write two equations is because we have two unknowns, the a and the b. So we're going to start by writing that. So we've got L of x is equal to, whoops. Sorry about that. We've got the L of x value right there, 3. So I'm going to say 3 is equal to a plus b. And I'm going to go ahead and do the natural log. So the natural log of 2, which is my x value. And so there is one equation. Then for the second equation, we would use the second data point here. And so we would say 7 is equal to a plus b natural log of 5. The next part says find the values of a and b. And so back in Algebra 1, we learned that if we had two unknowns and two equations, we could do that by solving a system of equations. So that's what I'm going to do now. I'm going to set up my system of equations. And so I'm going to put 7 equals a plus b natural log of 5. And I'm going to go ahead and subtract this second equation from that because the a value has a coefficient of 1 and this a value has a coefficient of 1. So those will cancel. So I get -3 is equal to negative a minus b natural log of 2. There we go. And so when I go ahead and combine my equations, that a and negative a are going to cancel out. And so we get 4 is equal to b natural log of 5 minus b natural log of 2. Now I've run out of space there, so I'm going to move up here. And so we've got 4 equals this. We are trying to solve for the b. And since it's in both terms, I'm going to go ahead and factor that b value out. So I factor out my b, and I have the natural log of 5 minus the natural log of 2. And so my last step here would be to divide by the natural log of 5 minus the natural log of 2. And I'm going to do that here as well. So the natural log of 5 minus the natural log of 2. Didn't leave myself a lot of space there. So now I can find my b value. I will use a calculator for this to get that value. And so I'm going to do our numerator over denominator to make it look exactly the way it does on my paper. And I get 4 natural log of 5 minus the natural log of 2. And I forgot my parentheses. Sorry about that. You can't see that very well. There you go. Okay. And so I hit enter, and there it is, 4.365. And so we have found the B value. So our B value is 4.365. Now, once you have the B value, then it's easier to find the A value. All you have to do is plug the B value here and then solve for the one variable. I'll go ahead and do that right here. So I get 3 is equal to A plus 4.365 times the natural log of 2. And so I would subtract this to get it to the other side. Let me go ahead and show you my calculator to show you. I don't round until the very end. That's what you should do. So 3 minus, I can go ahead and copy and paste this entire thing. So I highlight it and hit enter to make sure I'm taking the whole thing and then the natural log in 2. That way you keep that value until the very end and then you round. And so our A value would be negative 0.026. If we wanted to write the equation, we could now, since I have both my A and my B value. I get L of X is equal to the A value, which is negative 0.026, plus my B value, which is 4.365, natural log of X. And so that would be the equation right there that models this table. All right, so I showed you how to do that algebraically. We wrote the two equations, we did it as a system of equations. But in the past, we have learned that our calculator will also do that when we do regression equations. So they've given us a table above here, and they've asked us to write the equation using our regression capabilities. And so we want to write it again in the log, so we're going to use a regression of a log. So the first thing I'm going to do is go to Stat. I'm going to hit Stat, and then I'm going to go to Edit, and we're going to put in our L1 and our L2. So our L1 here is our church size, our L2 is the average salary. Now we get out of that once our data is in there. You want to make sure you type that in correctly because just one number will throw the whole thing off. Now you go to Calculate, and you're going to go down to where it says Log Regression. The natural log regression is number 9 on this calculator here, so I'm going to hit Enter. It's telling me X is going to be L1 and Y is going to be L2, which is what we want. For store regression equation, remember you do alpha trace Y1. That's going to get that equation written and put into the Y1 for me. And so now I hit calculate, there's my equation. And if I go to my Y equals, it's going to be there as well. So I'll go ahead and write that down here. And so we want that to be S of P is equal to negative 91.542 plus my B value of 29.909 natural log of P. It says, using the model found in Part A, what is the predicted annual salary in thousands of dollars for a pastor whose church size is 500 people? And so 500 people is being represented by this P value. So we are looking for S of 500. And so if you remember, since we stored this into our calculator here, I could hit alpha trace Y1 because that's where my equation is. And then I can put the 500 and the calculator will do the hard work for me. The other option is to go ahead and plug it in right there and simplify it that way. So we get 94.330. I rounded to 3 decimals right there. 3 decimals is the least amount that you want to leave on a problem. So make sure that you're rounding or truncating to that point. All right, here's another example. Our next example says the most common and preferred method to measure sound intensity levels is in decibels. The sound intensity level beta, of a sound having intensity I in watts per meter squared is modeled by this equation, where A and B are constants. The sounds of noisy traffic has an intensity of 1 by 10 to the negative 5 watts per meter squared and corresponds to 70 decibels. A loud concert has an intensity of 1 and corresponds to 120 decibels. Use the given data to write the two equations. So again, for the algebraic purposes, anytime they give us the 2 points, we can write the two equations. So that's what we're going to do here on A. And so we get 70 equals A plus B times the natural log of 10 to the negative 5 power. So that was my input right there. And then there was my output. So I just went ahead and put those in that equation. I'll do the same thing for the 1 and the 120. And so I get 120 is equal to A plus B to the natural log of 1. And so then again, we're finding our A and B value. This one's a little bit easier because if you remember, the natural log of 1 is 0. And so 0 times anything goes away. So we get 120 is equal to A. If you want to write that down on your notes, just to remember that, I'm going to go ahead and put the B times 0 there. So 120 is equal to A. To find the B, we just plug that in. And so we get 70 is equal to 120 plus B to the natural log of 10 to the negative 5 power. I subtract the 120. And so we've got B natural log of 10 to the negative 5 power. And so we're going to divide by that. And so that's something we'd expect you to do on the calculator. So we get negative 50 divided by the natural log of 10 raised to the negative 5th power. Whoops, got an extra parentheses going here. And so we get 4.343. And so there is our B value. It tells us on the next part here, the human eardrum can burst when sounds reach an intensity level of 1 times 10 to the fourth power watts per meter squared. According to the model found above, what is the predicted number of decibels required to burst a human eardrum? Okay, so we are looking for beta of 10 to the negative 4 power. Sorry, positive 4. 10 to the 4th. And so we're going to plug that into our equation. So we found A was 120, and then B was 4.343 natural log of 10 to the 4th power. And so in this case, we're looking for what that's equal to. Again, you would want to use the calculator for that. And so we get 120 plus, I use that whole thing, so copy and paste, and then the natural log of 10 raised to the 4th power. And so that is 160. And so there we go. That's what would cause the human eardrum to burst. All right, so we looked at some logarithmic models, and now we're going to look at a different way of modeling it as well, with the semi-log plots. And so we did introduce you to that in the 2.9 section. Now we're going to go just a little bit deeper. It shows us here that semi-log plots look a little bit different. In a semi-log plot, one of the axes is logarithmically scaled. In AP Precal, we will only be scaling the vertical, the y-axis. So instead of having the same on the x and the y-axis, on the y-axis, we're going to logarithmically scale it. Exponential functions will appear linear when we do that. So here's an example of a population growth. And so we've got this model here. You can see this is exponential on the regular graph, as we have just regular y values. When we change this to logarithmically scaled, so a base of 10 in particular, then it looks linear here. And so it helps us with data collection in looking at where each point is, because a lot of these points look exactly the same until it starts to get a little higher. But here we have a better idea of where our points are. That's why that semi-log plot exists, is just to make that data a little bit easier to review. And so this is one that we saw earlier. These two graphs, it says previously we looked at the two graphs displayed above, displaying the population of English Americans in the current United States. from 1620 to 1820. The graph on the left shows the population using a normal scale on the vertical axis, and the graph on the right is a semi-log plot where the vertical axis has been logarithmically scaled with a base of 10. We've done that one. So in example 1, we're going to use the features of the semi-log plot above to justify why an exponential function is appropriate for the population of English Americans in the current one. And so all we're saying here is the exponential is a good way to look at it because when we scale it logarithmically, we see that linear equation. So the semi-log plot looks linear. And so that tells us that it is appropriate when you change the exponential to the logarithmically and it has that linear look to it. That is a good model. All right, so this next one then says, after Mr. Passwater tells another one of his hilarious math jokes, it begins to spread around the school. The number of people, P, that have heard the joke after 2 minutes is graphed on the semi-log plot above, where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for P? And so first off, we see that it looks vertical, so we know that it is going to be an exponential graph. So we can throw this one out right here. When you are scaling the y-axis is only, so we've got it here scaled by 10, then it makes that line, then we know it's exponential. So we can throw that one out. We can also throw this one out because this is linear. It has to be one of these two exponential graphs that we're looking at here. I think it makes it easier if we go ahead and pick out some of these points. And so to practice with the semi-log, this is 0 is my x value. That one's easy to see. But with the semi-log plot, remember, this is 1 right here. This would be 2, 3, 4, 5. So each one of these lines is by 1 getting up to 10. Now, to get from 10 to 100, each one of these lines would be by 10. So this is 10, 20, 30, 40, 50, 60, and so on up to 100. And then these would go by hundreds. So my first point here is at 0, 2. My next value of 1 here, this is 1, so this would be 2, 3, and 4. And we'll go ahead and get one more at 2 right here. It is at 1, 2, 3, 4, 5, 6, 7, 8. So we've got one at 2, 8. Now you should recognize these numbers as exponential, and it should be easier to see. So at 0, it is 2, so we know that's the initial amount, and it is being multiplied by 2 each time. And so D makes that the correct answer with my initial amount and my common multiplier of 2. All right, some important notes about semi-log plots. When we logarithmically scale the vertical axis for a semi-log plot, we are not changing the actual y values of the data. To logarithmically scale the vertical axis means that equally spaced values on the y-axis are proportional, whereas equally spaced values on the x-axis are linear. So we are not changing the data there. All right, so here's another example of what could look like for a semi-log plot. They give us this data right here, and it says the table above gives selected values for the function f. Which of the following graphs could represent these data in a semi-log plot? And so when you're looking at here, you can eliminate some of them because they are not done with a logarithmic scale. Now this just shows the 1 to 10, so that would work. But if you look at this data point, 140, this is not 40, this is between 1 and 2, and so this would be a decimal value. So that doesn't work. Same thing here, 1, it is at like 1.6, so that still doesn't work. Both of those would be thrown out pretty quickly. On this next one here, we are looking at our data points. And so we want the semi-log plot. And so this is what you should recognize as our semi-log plot. And it is at 140 and then 260. So at 1, this is 10, 20, 30, and 40. So, oh, you can't see that. So this is 10, 20, 30, and 40. So that is correct. At 2, it is 60. So this is 10, 20, 30, 40, 50, 60. At 3, it is 90. So we get 10, 20, 30, 40, 50, 60, 70, 80, 90. Our next one is at 135. And so 4 here is 100. This would be 200. And so there's my 135. And then my last one is at 5 and 203. And so you can see this is 5, 100, there's 200, and that's really close to it. So D would be the correct answer in this case. For our last couple examples here, we're going to actually plot the points ourselves. So in this case, this is my X value, this is my Y value. Again, this is scaled logarithmically. So my first one is 0 and 200. And so I'm going to get 0 is right here. This is 10, this is 100. And so the next line would be 200. So this point would be right here. I'll do another one with you and then go ahead and pause it and try and graph these. And so this is 1 and 25. So 1 is right here, 10 is right here, 20 would be my next line. And so 25 would have to fall in between these two because this would be 20, this would be 30. All right, try and sketch the other ones to see if you can come up with the plots and then go ahead and unpause and see the answers to check your work. All right, so check your work there. This one was kind of tricky right here, the 4.6. And actually I've got it leaning over a little bit. 4.6 and 1.5. So 4.6 would be right here. And then 1.5 is in between those. Remember, 1 is this bottom one, 2 is right here. So 0.5 would be in the middle. The rest of them were kind of easy to do. So just check your work there. As we move further, it tells us, as we have seen, if we graph an exponential function on a semi-log plot, the graph will appear linear. In these cases, we can create a linear model for the graph of the semi-log plot. And so here is our linear model of the semi-log plot. It tells us y is equal to log base n of b, x, plus log base n of a. And so basically this is our rate of change, our slope, because if you remember from Algebra 1, a linear model is slope times x plus our y-intercept or our b value at the end, the mx plus b. That's what this is right here. It tells us to note that the slope of our linear equation is log base n of b, and the y-intercept is log base n of a. The base n corresponds to the base used for the scaling of the vertical axis. So right here, we see this has been scaled by 10, and so we would use the common log for this one. Okay? So this part right here, it's going to be 10 because the y-axis is scaled that way. All right, so it tells us that this semi-log plot corresponds to the data in example 3. And so if you remember example 3, that was this one right here. And we had already picked this graph right there. So that's the one that we picked on D. But right now we're going to focus on this table right here. So it says 1, 2, 3, and then it gives us our data points. Well, it told us right here in our description that the slope of our linear function in log is the log NB. We already know this is 10. And so my B value is this log part here is going to be the average rate of change, basically. So we would take our y value and divide by our x value here. So 60 divided by 40. And so that gives us 3/2. And so our y value is going to look like log of 3/2 x. Then for our other part, that's our y-intercept. So we need to find what it would be at 0. So we would have to work this table backwards. So we're trying to get this 0 value so we could get that y-intercept. And so I can take my calculator here. And so when we discovered we're multiplying times 1.5, 3/2 to get to each one of these. So I would divide to get back this way. So I'm going to divide 40 by 3/2. And so we get 80 over 3. And so that is plus log of 80 over 3. All right, so let's summarize kind of what we did there. We used the common log of base 10 because that's what it's vertically scaled by. We found our common multiplier or average rate of change to do this portion here. And so we've got log of 3/2 x. Then we found our y-intercept, which is log of 80 over 3 there. It says using the linear model from part A, write the equation of the exponential model as in the form y equals a times b to the x for this data. And so we said this right here, this 3/2 was our common multiplier. So we know that's our b value. So that's what's going to go there. And then we want our initial value to be that a value. And we said that's the y-intercept. And so that's going to be 80 over 3. You can always check your work once you have written it. We can go right here. I can put in my 80 over 3 times my 3 over 2 raised to the x power. Now I go to my table and I can see 0 to 80 over 3, but there is 140, 260, 390, 135, which was exactly what we had right here on our table. Okay, so that was a semi-log plot. Hopefully you get comfortable working with just the different types of context to write the equations and graphing it to show the models.